Okay. Hello students. Today our topic is dual nature of light. So we'll discuss about the wave particle duality of matter. So you can say that light have a wave character as well as a particle character, and depending on the situation it can behave more like a wave character, and at the other time it may behave more like a particle. You may have studied Young's double slit experiment, and it shows interference. We know that interference is a phenomena that is observed only when light behaves as a wave. And similarly, we also have observed photoelectric effect, in which light is somehow behaving like a particle. So there are some phenomena which can only be explained sufficiently when light is shown to be a particle. Like I would say, yeah, the photoelectric effect, for example, means we will come into it, but just before that, let's discuss what happens. So whenever some light is incident on a metallic plate, what happens? It kicks off electrons from here, and this kicking of electron is highly dependent on the wavelength of the light. Means if wavelength of light has, suppose, this much of energy, suppose this much of energy, what happens? It kicks off one electron. So let me try to show it some kind of graph. This is able to kick off the electron. At the same time, this one is not. And if I say this one, definitely not. What about this one? This one also kicks off. What about this one? We can compare this one and this one. You see that this is more than the double of energy here, but still this is also kicking off only one electron. One wavelength, one electron. Then what happens here? We are talking about the transition of electron from its stable state to its free state. So that means that here the particle, sorry, the light wave, or say light itself, behaves like a particle because it is kicking off, or it is some kind of behaving like a colliding particle. Because had it been wave, it would have provided enough energy to kick off two electrons because it has double the energy, right? But it is not happening that way. So this is how we can say that here light is behaving like a particle, less like a wave. So let me try and write down one question that will start us with here. So I have one question with me. A photon not this one. So let's say consider a parallel beam of light of wavelength. So the wavelength is considered to be 600 nanometer, and it is a parallel beam. And again, it has an intensity 100 watt per meter square. You know what is the intensity? Intensity is the energy incident upon an per unit area. So this is the intensity of this parallel beam of light. I'm taking this example from H.C. Verma book, and we'll try to work it out. Now, first question is, find the energy and linear momentum of each photon. Energy and linear momentum. Of each photon. And the second part is the energy crossing 1 centimeter square in 1 second, that the question says to us. So we have, this question is not a big deal. You can see that we have already given the energy intensity part here. Using this we can relate with the surface area, because the surface area is given as 1 centimeter square, and using that we can find the energy. But first let's consider the first question, part A here. So you could see it is asking for energy and linear momentum. Do you remember the energy formula for a photon, light photon? E equals to h nu, nu being the frequency, we can simply say hc by lambda, or h. I'm writing again the symbol of frequency as f to avoid any kind of confusion with v looking as nu, so hf, where c by lambda is equal to f, or simply c equals to f times lambda, where all these three are parameters of light: c, speed of light; lambda, wavelength of light; and f, frequency of light. So we will be using this equation here. I think you can see this here. Yeah. So the energy of each photon we can find out using this equation. So what is E? What is F? Oh, I'm sorry, we don't have F, but we have C. We know the value of H. What is H? Planck's constant. So the value of H is 4.14 into 10 to the power minus 15, and the unit is electron volt second. We can skip the unit for now, because we know if we are working with all the SI units, our result will definitely come in SI units, that is for joule. So be confident of that. That's the benefit of using one system of unit at a time, and it's always beneficial if you're using SI units. So first convert all the units into SI, put it into the numericals, find out the value in SI, and then convert in whatever you need to convert it into. So second, the speed of light, the very famous number 3 times 10 to the power 8, again SI unit, meter per second. Now lambda, what is the lambda here? It is 600 nanometer, and what is 1 nanometer? 10 to the power minus 9 meter. Again, meter is the SI unit. We would be using 600 into 10 to the power minus 9, or we can write that 6 into 10 to the power minus 7 meter. By solving, we would be getting, I don't have a calculator right now, but what I could do, simply say 3 gets cancelled 2, and that's how we are getting times 17, that's 15. Okay, one thing I missed, we don't have all SI units here. Here we have electron volt second, so let's keep it here, meter per second, and here meter. So that's a mistake from my part. Obviously we can use that thing. We can always convert all units into SI units and then use that in our numerical, but here we need to be careful. So this will give us our answer as electron volt, not in joule. So this comes up 2, and this is 2.07, 10 to the power 15, 17. It is getting cancelled off, so 2 to the power 2.07 electron volt. Yeah, that's our answer. So this is not what we are studying today, right? We are studying the photoelectric effect, but basically before going into that, these are the small numerical parts that we will be covering. The second part was the energy crossing 1 centimeter square, means the energy received by 1 centimeter per centimeter square in 1 second. So what is intensity? We already have this value of intensity here, right? This is 100 watt per meter square, so we can use this value. But before that, what is intensity? Intensity equals to energy per unit of time, means power delivered to an area divided power delivered to per unit area. So area. Now did I write it like that? So energy by time divided by area. Now it is asking for 1 second. We can write here 1 second. We can write the area 1 centimeter square, and we can write the intensity, and we can solve for energy, right? So using that, we are getting energy equals to intensity times area times time. What are those? Our intensity is 100 watt per meter square. Area is 1 centimeter square, that is 1 divided by 100 times 100. Let's put this comma here. 10,000, 1 divided by 10,000 meters square into time, that is 1 second, right? We are getting 100 times 1 divided by 10,000, that is 1 by 100. 100 watt times second, that is joule. We are getting 1.0 into 10 to the power minus 2 joule, right? I think this should be easy for many students, and if it is not been easy, you should be benefited with it. And using these two, can you find out the number of photons that is falling on this area per unit of time, or say per second? That's the third part of the question. I would definitely point that out in the chapter of H.C. Verma. So I'm keeping it here for my reference so that I could see it. And now, so the number, let's say we are taking this number, and what is n here? N is the number of photons falling on per centimeter square in 1 second. Means we have already calculated the energy to be 1 into 10 to the power minus 2 joule. Energy is equal to 1.10, 1 times 10 to the power minus 2 joule. And we have also calculated the energy per photon. Energy per photon equals, that was I think, I didn't use calculator, but I think I should remember that is 2.07 electron volt. We have a conversion mode, right? Using that conversion ratio, we can find this value into joule. So 1 electron volt equals 1.6 into 10 to the power minus 19 joule, right? This is very easy to remember. If you recall the amount of charge on an electron, that is 1.6 into 10 to the power minus 19 coulomb, and this is the same, using the same concept, like somehow electron volt is related to the charge on electron. That is 1 volt of electron. One electron takes, if one electron crosses 1 volt barrier, it crosses the energy of 1 electron volt. So using the same concept, 1 joule is related to 1 electron volt, and that is how 1 electron volt equals to 1.6 into 10 to the power minus 19 joule. So we can use this conversion and we will get 2.07 into 10 to the power minus, sorry, I missed 1.6, into 1.6 joule, and that would come out to be around 2.6. That would be around 3.3 something. Yeah, so let's take it this way, into 10 to the power minus 19. Now our question is, the question is how many photons are falling on that 1 centimeter square area in 1 second. So that would be, we know the energy of photon. So how many photons will group together to make up for this energy? So that would be n equals to E divided by E photon. I'm just taking E photon as this imaginary situations where the photon has wavelength 600 nanometer. So that is coming out to be 1.10 to the power minus 2 joule divided by 3.3 something into 10 to the power minus 19. That will come to be around 3 point something, because into 10 to the power 17. Am I right? No, that would be, if I take 10 here, that would be 10 to the power minus 3. So that would be 10 to the power 16. So this number here would be around 3 point something, 3.0. If I use calculator, I would be more close. It would be around 3.0 something into 10 to the power minus 19. Sorry, 10 to the power 16. This is the number of electrons. This is a large number of electrons. So using this, and I think we also had one question that we are missing here. Let me recall that question. Part A. Yeah, we also had to find the linear momentum. And how do we find linear momentum of a photon? We already know that photon has energy hc by lambda. And momentum of a photon is given by linear momentum of the photon equals to energy of the photon divided by the speed of the photon, E by C. That gives us h by lambda. This is the same scenario. We can again put up the values. We know the value of h, 4.14 into 10 to the power minus 15 EVS, EV, and electron volt second, and lambda we know here is 6.600 into 10 to the power minus 9, that is 6.0 into 10 to the power minus 7 meter. Using this, we can get the value to be electron volt second divided by meter. Yes, so that would be, our unit would be something like EVS meter inverse, and this value would be, let's first clear out 10 to the power minus 8. That would be the multiple of 10 here. And what is 4.14 divided by 6? So this is around 7 times 6. It should be around 7, but yeah, 6 9 something. Oh, it's absolutely 6 9 getting. Yes, this is 0.69 10 to the power minus 8, or we can write in scientific notation 6.9 into 10 to the power minus 9 electron volt second per meter square. Again, we can convert this into SI unit, that is kg meter per second, by using the conversion ratio 1.6 into 10 to the power minus 19. So after we get the concept, means you already know these things, it was just a buffering, just to remind that every wave has some momentum and every light particle has some energy associated with this. We came out to recap these things. So now, using these concepts, we will try to explain what is photoelectric effect. So the basic concept of photoelectric effect is whenever light falls on a surface, it has some effect on the electronic structure of the molecules or the atoms lying on that surface. What happens whenever light wave or the photon falls on a nuclear structure, atomic structure of a particle, it kicks off one electron by giving it enough energy to escape, or may not be, it might not be enough to escape, so it will go up to a higher stage and come back emitting some of its energy finally. So to have this much of energy to kick off an electron, one light should have such that would be energy that we call E naught. So this is the minimum energy to kick off an electron, and that would be considered to be Hc. You know, H is constant, C is constant. What we could change? We could change the lambda. So for that, lambda would be termed as lambda naught, or if we are simply assuming it H times frequency, Planck's constant times frequency, we can simply say H frequency naught. So this is how we could find out our threshold frequency. Now what is threshold frequency? This is the threshold energy. And this is the threshold, let's say threshold frequency. So threshold frequency is related to threshold energy in the same way a frequency of a wave is related to the energy of that wave. If a wave has exactly the threshold frequency, it will have exactly threshold energy, and it will be kicking off one electron, exactly one electron. Now the question is the threshold energy is a definite amount of energy for every kind of matter in order to kick off that electron and send it, make it free for every type of matter? Answer is definitely no. There are several types of matter. If you are using an iron plate, you are using a silver plate, or you are using a gold plate, the energies would be different because they have different attraction to the electron, they have different electronic configuration. So now let's say what happens when that photon, means that photon which is incident in the form of light on that metal plate, has larger energy as compared to this threshold energy. So let's say that electron has double the energy of that threshold. What would happen? As we discussed, it will not kick off 2 electrons, but suppose this this photon has some energy that is 2 E naught. We already discussed we are keeping E naught as the threshold energy. So EP equals to T naught, 2 E naught. What happens? This energy is divided into 2 forms. First, the first part is helping in ejecting the electron, and the second part will impart to the kinetic energy of the electron. Means if you are ejecting the electron with E naught energy, that is the threshold energy, it will simply be kicked off without any energy left with us. It will be free, but it will not be an energetic electron. So to give it energy, it must have some energy greater than the threshold energy that photon should have. So what did I write here? Kinetic energy of the electron. So if you have some energy as a photon, which could be something, and you are using it to kick off the electron, then this would be the kinetic energy of that electron. So let's say this is a general notation to write. We write this E naught as phi, that is the threshold energy, and we write the kinetic energy as K max, means maximum kinetic energy of electron. So after considering all these factors, we will come to know that this kinetic energy, maximum kinetic energy, will be equal to what? The energy of the photon minus that threshold energy. And what is the threshold energy? That phi. We have come to final conclusion that we are keeping phi as the notation for threshold energy. So, and EP is hc by lambda. Can we say it is lambda p, or leave it lambda? Okay, hc by lambda minus phi. I hope this much is clear to you. Using this, you can find out, you can try to solve some numericals. So let me find some numerical. I might have something with me. Yes, I have few of the questions. So let's say again a question from H.C. Verma. Monochromatic light source operating at 200 watt. Always try to find out the useful information in your numericals so that you can use it to solve that. So it is monochromatic light source. What is monochromatic? This is a good thing to understand. Whenever you hear this thing monochromatic, that means that light source, monochromatic source, is ejecting or say emitting a light of same frequency, same wavelength. Means obviously if the light has a constant frequency, it will have constant wavelength. So in our question it says a monochromatic source of light operating at 200 watt emits 4 into 10 to the power 20 photons per second. Let's write that. Find the wavelength of light. Means we know that the power of this light is 200 watt, and we also know that the number of photons sent per unit second is 4 into 10 to the power 20. So how many what is the wavelength of this light? So first find out the energy of this photon, right? Energy of this photon equals to energy emitted by this light per second, energy per second, which is power, divided by the number of photons per second. This is the energy per photon. We are getting E per second, that is the power we are getting is 200 joules per second to be more specific, and number of photon per second is a number, right? So number per second, so 10 to the power 20 per second, we are getting 200 by 4 into 10 to the power 20 joule. This is energy for one photon, and the energy comes out to be that we 50 times 10 to the power 20, that would be 5 times 0 into 10 to the power 19 joule. Now using this, we have E 5 into 10 to the power minus 19 joule. We can find out what is asked. They have asked to find lambda, right? And we know that EP equals to HC by lambda, so HC by lambda equals to 5 into 10 to the power minus 19. Did I say minus? It should be minus, yes. And using that, we can simply say lambda equals to HC divided by this value. You can exchange these two. What have I written? HC by 5.0 into 10 to the power minus 19. So we can calculate these things, right? Now we can use the value of H in SI unit. That would be easier for us, and that is 6.6, that is 6.63 into 10 to the power minus 34 joule second. Yes, if I'm not wrong, I could use a calculation. That is 4.14 into 1.9 to 10. Yes, this is approximately the same value, 6.63 into 10 to the power minus 34 joule second. And C is a very easy value. We all know that 3.0 into 10 to the power 8 meter per second. And the denominator is always known to here, 10 to the power minus 19. Why don't we write the unit here? So all units are in SI. We are confident to get the unit in meter here. So if I solve it like that, 6.63, this is coming out to be 6.63 into around 20, but it will be less than 20. Yeah, this will be 19.89 into 10 to the power minus 26 joule meter divided by 5.0 into 10 to the power minus 19 joule. That gives us around some meter, so that will be 3.9 7. Oh, it will be closer to 8. So 3.98 into 10 to the power minus 7 joule. We can always convert this oh, sorry, what did I written? This is not joule, this is meter. Here it is meter. So we can always convert this in what do you call, nanometer or angstrom, which is to be easier. So if I convert this in nanometer, we will simply multiply this with 10 to the power 9, and that gives us 398 nanometer. So that should be our answer. So and that was asked for. Let me find out some more interesting question that we can work. But one more thing that we can discuss here, we just discussed about the linear momentum, and we know linear momentum of light photon is nothing but h sorry, what did I say, h by lambda. Why h by lambda? Because this you can relate this way, P equals to energy of that photon divided by the speed of that photon, and we know that energy of that photon is hc by lambda divided by c. That comes out to be here, h by lambda. And using this we can relate lambda with h and p. So if we are given the linear the linear momentum of that photon, we can find out lambda using lambda equals to h by p. And if we know the wavelength of that photon, that is lambda, then we can find out p, that is linear momentum of that electron, using this equation lambda equals to h by p. You have also heard about de Broglie wavelength. So this is the equation you can use in de Broglie wavelength. Means I have somehow gone disorganized in this session. I'll try to organize myself better in this in the next sessions. But before I go, let me help you in this part. Like, there are some matter waves, means matter behave like waves, waves behave like matter. So whenever we know the speed of a matter, if that matter is behaving like a wave, we can relate them in this formula. If that matter has a linear momentum 1 kg meter per second, we can find out the lambda using this. Means the wavelength associated with the movement of that matter would be lambda h by p. We know h equals to, what did we did, 6.63 to 10 to the power minus 34, right? That is joule second, divided by p. We just said it is 1 kg meter per second. It's a fictitious value. You could have different kinds of values. 1 kg meter per second. So in that case, the lambda associated with that motion would be 6.63 into 10 to the power minus 34 joule. That would be, okay, that would be meters, right? And if we convert it, would it be meters or something else? Let me see. Joule second by 1 kg meter per second. Yes, that would be meter, because joule can be written as kg meter per meter square per second square, and we are getting cancelled. Kg by kg meter square getting cancelled as meter second 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 square. Means joule second per second square, that is giving us kg meter square per second. Whether this is not so critical here, we can simply find out using our calculation that the unit we are getting is meter. So this is how we can find out the waves of wavelength of a matter wave using this formula, that is lambda equals to h by p. You can always explore more about these things on Toppr videos. We have extensive videos in every parts of physics, and if we don't have, we are trying to cover that as soon as possible. So goodbye and have a great learning, and all the best for your exams. Okay, goodbye.